Hello and welcome back. We're going to do lesson 2 of unit 2. We're going to fall off a log today. In our jumpstart is to remind us how we transform functions. The function that's listed right here is quadratic. It's a parabola, but it's been modified. So the original one, we kind of know how that goes. It goes through 0, 0, up 1 and over 1, up 3 and over 1, up 5 and over 1. That's the shortcut. And then reflect across the y-axis, and very quickly we get a parabola. How has it been modified? Well, for one thing, it's been shifted horizontally. X plus 1 will shift it left 1 unit. Now you might think it's right 1 because it says plus 1, but this is backwards. So it goes to here, and then there's a plus 3, so that goes up 3, 1, 2, 3, to here. So the origin has now moved to there. And then finally, the negative out in front flips it completely upside down. So now it goes from this new point at negative 1, 3. It goes down 1 and over 1, down 3 and over 1, down 5 and over 1. And we have a new line of symmetry across this line here. And so if we reflect those points, we get our new parabola. In a similar way, exponentials will transform. So in number 2, here's our original. So some key points for that would be 0, 1, 1, 2, 2, 4, 3, 8, 7, 8. And of course, there's an asymptote coming down here like that. This new exponential is the same points moved down 3 units, including the asymptote. So the asymptote is down 3 units. It's moved down to here. And we move every point down 1, 2, 3. Okay, so that's the key to doing transformations. Now let's jump into the lesson. X, and let me get this with the inverse. The inverse is 2 to the x. Okay, and the last two values I'm going to choose for negatives. Negative 1, 2 to the negative 1, and that's 1/2 or 0.5. 2 to the negative 2 is going to be 1/4, 0.25. So now reverse the points and reverse even these last two. We have something to graph. So we're coming off the asymptote and we're going this way. So a key feature there would be, where's the asymptote? It's on the line x equals 0. What's the y-intercept? There is none. What's the x-intercept? It's 1, 0. We'll do x with the inverse. And how about just the inverse? Remember, is going to be 3 to the x. This would be 1/3. This will be 1/9. And as a decimal, 1/9 is about, we'll just leave it at 0.1. 3 to the 0 is 1. 3 to the 1 is 3. 3 to the second is 9. 3 to the third is 27. That's going to go off the graph. Now we're going to reverse and go x with f of x. And you're going to get x with f inverse of x. That'll be 10 to the x. Flip it around. And then we don't How did you decide what values to use for x in the table? From the inverse, how did you use the x values to find the y values in the table? I interchanged from the inverse. What similarities do you see in the graph? Same x-intercept, same asymptote, and the same general shape. What differences did I observe in the graphs as the base got higher? The graph became flatter. And I'm talking about across the top there. What is the effect on the graph of changing the base on the graph of the logarithmic function? And you could call this the rate of growth. So the effect of the graph change on the base is it changes the rate of growth. Okay, so now we're going to look at common log. So we can use technology, we can use our calculators now. Use technology to graph this. That means Desmos. Okay, so as you do that in Desmos, how does it compare to the graph you constructed? Well, hopefully the same. How do you predict the graph of y equals a log of x will be different from the graph of y equals log of x? That should be a vertical shift. Test your prediction by using various values of a. What is the effect of a on the graph? Okay, so you have to look and see this happen. How do you predict that the graph of y equals log of x plus b will be different? This will be a horizontal shift. Test your prediction with various values of b. What is the effect of adding b? So positive b, it makes it go left, and negative b, it makes it go right. What will be the effect of subtracting b? This should be down here. Make a general argument for why this is true for all logarithmic equations. Horizontal translation works for all functions. So as you look at these two graphs and try to figure out what change has been made, notice that there's been a shifting of the asymptote. It usually would be around here for this one, and you'd have the point 1, 0. But this one has moved 1, 2, 3 spaces to the left. So this is probably x plus 3. And this graph, its asymptote has moved 1, 2 spaces to the right. And the point I would expect to be at 1, 0 is now down here. And that means it's been shifted down 2. So if I combine those together, right 2 and down 2 should look like that. And graph these following functions. So this is going to go up 2, and this is going to go right 1. So 1, 0 is now up 2 and right 1. The asymptote has changed to the right 1. This has gone down 1, left 2. So the asymptote is now over here. 1, 0 has therefore moved 2 spaces left, and 1 space down. Compare the transformations of the graphs of logarithmic functions with the transformation of the graphs of quadratic functions. What similarities and differences do you observe? The vertical and horizontal transformations work the same. With a quadratic function, the vertex 0, 0 is often used as a reference point. With logarithmic functions, the point 1, 0 is used as the reference point. Features of a logarithmic function. The domain is going to be normally 0 to infinity. The range is going to be all real numbers. The reference point is going to be 1, 0. The vertical asymptote is going to be the line x equals 0. It is going to be continuous, and it increases from 0 to infinity. So to make a quick graph, what you want to do is ID the transformation, redraw the x-axis and asymptote, and then mark your new reference point. Where has 1, 0 gone? Okay, we're going to go ahead and stop right there. Have a great day.